enthusiast knows Dr. Passey and his past works. But for those who don't know him, Dr. Passey worked as a petrophysicist for ExxonMobil for more than 30 years. He has a PhD degree in planetary science from California Tech University. During his career, Dr. Passey developed new formation evaluation methods that you will find in many commercial softwares. One of his well-known methods is the DlogR source rock evaluation method that he will be presenting today. So thank you very much, Dr. Passey, for accepting the invitation, and the mic is yours.
Okay.
So, please, if anyone has any question, please write it down in the chat box, and he will answer it at the end of the presentation.
Well, I appreciate the invitation, and you were -9 degrees Fahrenheit this morning. I'm currently at 70 degrees where I live, so I am glad to join you by computer today. You have my presentation. I did take out about a half dozen slides because I thought this is going to go forever, and you can just log off when you get tired of hearing me. I changed the name. I'm going to talk about source rock evaluation from well logs over the last 4 decades. And a technical tipping point is when something becomes so obvious that you put all the pieces together and it makes a big change, even though people knew all the pieces to the puzzle beforehand. It's how you package it that then it becomes something really changing. Even though I'm presenting this, in this slide, there's 3 publications where the majority of the slides that I'm going to show come from. Everything is in the public domain, but it was really a group effort with a lot of different people: Steve Creaney, Gene Culla, Kevin Bohax, a lot of people that really contributed to this work. Let's see. Field safety. I went out and I've spent many weeks out in the field looking at source rocks all around the world. And I put in this picture. It wasn't staged, but this is Dr. James McQuaker and Remus Lazar, and we were out on the Maori Shale, and I was making uranium, thorium, potassium measurements. And when I saw this, he's actually back about 5 or 6 feet, so it's not as dangerous as it looks on this picture. But I thought, well, that makes it good. So when you are in the field, do be safe. A little bit of an overview. Again, you're familiar very much and working in the Bakken Formation. I will talk briefly about it. I've worked in probably close to 60 or 70 mudstone formations. Initially, we started out working just looking at them as source rocks. We wanted to know, is there a source? If there's no source in a basin, then there likely are not going to be any hydrocarbons reservoired. So the DlogR technique was set up as a purely exploration tool. I will talk briefly on the Marcellus, Eagle Ford, the Barnett. I'll show examples from it. I'll show examples from the Woodford. I'll show examples from of the Muskwa, Ottawa, up in the Horn River Basin, and then down in Alberta, some things that, and I've also worked quite a bit in the Monterey Formation, which can be a similar, type formation. Here, I spent a couple of years in Alaska, and Prudhoe Bay Field is one of the largest conventional reservoirs in North America. Its dimensions are, about 15 miles north to south and 40 miles east to west. And, in a traditional thing, it's got about, 25 billion barrels of oil in place and 26 or 46 trillion cubic feet of gas. And in a conventional reservoir, we have water, we have oil, and then gas. And with basic logging, we look at the gamma ray log oftentimes to identify what are our potential reservoirs. We look at resistivity to see, is there any indicator of hydrocarbons? And then we'll use like a neutron density crossover to see, do we have indication of gas or is it water? Things like that. And we can, interpret this and we can quantify the results. In terms of an Archie equation or a Shaley-Sand equation or something else. Now, this is in your neighborhood, the Bakken Shale. And again, you're very familiar with it, main production center part of the basin. And, and this is something that Fred Meissner was kind of the father of the Bakken Shale. He made some terrific observations about when you got near the deeper part where it was mature, the resistivity in the shales went up. And these are things that I built on. But just to bring things back, this large, mega billion barrel oil and gas field in Alaska, that's the size of it compared to the Williston Basin. And so the Williston Basin offers a lot more footprint on where to explore for. The problem is with all unconventionals is they are generally much thinner, lower porosity, and the permeability is really rough, very low. So just as some organic geochem basics, most people, and if you're in the petroleum industry, whether you're a geologist or a petrophysicist, you're aware of, this is the modified Van Crevelen diagram where we've got hydrogen index, which against oxygen index. And these originally were measured on elemental, but we used Rocky Valve pyrolysis, the S1, the S2, the S3 as proxies for these. But the type 1 and type 2 kerogen are oil prone. Type 3 is woody coaly. And type 4 is inertinite, which is, it's left over from like forest fires in the ancient rock record. There's really no hydrocarbon potential. But if you're type 1 and type 2, then it'll generate oil. Type 3 will generate primarily just gas. And if you're familiar with the Rocky Valve pyrolysis, again, there'll be an S1 peak, an S2 peak. And when things are immature, there's almost nothing. S1 is generated hydrocarbons, but the S2 is, if it's immature, it's all potential. As you get to higher maturities, you start generating more, excuse me, initially oil. And what happens, they'll talk about the Tmax temperature as an indicator of maturity. And what happens is then the S2 peak comes off at higher and higher temperatures. The Bakken is in the oil window, and there's very little shale gas that's associated with it. So the delta log R method, again, it was developed in the very early 1980s in the North Sea. This is the Kimmeridge. When we look at the gamma ray, we have a high gamma ray. So we've got a hot shale here. We have a shale up above, a shale below, and we have a nice sandstone reservoir. The delta log R technique is it's a porosity resistivity overlay. And in petrophysics terms, you sometimes call this the F overlay. But when you overlay these in non-organic rich and non-reservoir, the two curves will track each other. When you get into an organic rich zone, there's a separation. And there's also a separation when you're into conventional reservoirs, whether they be siliciclastic or carbonate. I'll talk about what delta log R means, But from the simple overlay, we can see how rich, or we can see how thick our source rock is. And we can even tell that in this case, it's mature because the resistivity is higher than the background shale. But we'll go into that classification and characterization later. Now, when we were looking at it, we found, and again, this was in the Kimmeridge Jurassic of the North Sea, when we plotted total organic carbon, and that's weight percent is how it's measured, usually during a LECO TOC, or you can also calculate it from a rocky valve pyrolysis. But there is a relationship between the sonic porosity, the density measurement, and the neutron porosity measurement. And when we go to higher TOC amounts, the sonic velocity goes down or the delta T goes up. And some people have used this as an indicator of organic richness of TOC. The density, because the organic matter is much less dense than the rock, the density will go down as you get higher TOC. And that's kind of well known. And even the neutron porosity goes up because the neutrons are measuring the protons that are in the material, and hydrocarbons, organic matter has a lot of hydrogen in it, and so there'll be a relationship there. The model that we had put together, again, we published on in 1990, but it was very simple, saying, if we have any rock, there's the solids that were deposited, and then there's porosity. And initially, most of these rocks are deposited in water, whether it's lakes or the marine environment. And so in most cases, the porosity that's originally there is water. Now, when the kerogen is deposited, it is deposited as a semi-solid, and it's deposited as part of the rock matrix. A lot of people try and put the kerogen into the porosity because all the porosity logs see the kerogen. It looks like porosity, but it is not part of the porosity system. And if it's immature, the porosity is still full of water, so the resistivity will still read low. Now, once we start converting that kerogen into hydrocarbons, whether it be gas or oil, then it will go into the pore system. Hopefully, for conventional reservoirs, much of that will be expulsed and migrate into conventional reservoirs. But there still is water in the system, and then there are hydrocarbons in there. Now, we're going back to this simple example. When we do this overlay, we then will quantify the separation here, and I'll talk about the calibration a little bit later, or you've seen it in the papers. But then, the magnitude of the separation is related to total organic carbon, or it can be calibrated to it. Now, when we look at this, in the reservoir, we have a lot of separation, but we usually use a gamma ray cutoff because we're not wanting to predict TOC in the reservoir interval of conventional reservoirs. The scaling that was used is a very simple, the technique was developed to be used at well site when they had the old film recorders. And so you'd be at well site, you'd plot off the resistivity, and then you had the sonic and the scaling that we used, and you can read about it in the appendix of our 1990 paper, but we just used an approximate scaling of a -1 to 50 as the range where these things will kind of track. When you're very tight on the left side here, it will not track. You'll have to do another kind of scaling. And if you're very undercompacted, it also will not track exactly. But again, go to the appendix of this paper to see more detail. Now, the Archie equation, most of you would be familiar with it. And, it's, again, Gus Archie, who worked at Shell, that was a tipping point. It was empirical, but he then tied the thing to a number of parameters, the water saturation, which we're interested in, the water resistivity, the porosity, and the deep true resistivity. Now, here, this is an example of a organic rich shale in the Paris Basin. We have a gamma ray curve here increasing to the right. So I've got shale here. I actually have tight carbonate up here. I've got some shale here. I've got a resistivity. And again, in the scaling, I've got one cycle of resistivity or 2 cycles of resistivity is 100 microseconds. And this is the sonic. And so I can take but what do we know in these shales? Well, number one, we don't know the water saturation. We have no idea what N is in the shales. We have no idea what the water resistivity is even in unconventionals, very little produced water occurs. We don't really know what the porosity is because our porosity curve is affected by the organic matter. So all we know is what the resistivity is. And so again, in the very simple technique, we will go in and do where we'll baseline in a non-organic rich shale. So we are in high resistivity. And then the organic rich shales pop out. Now down below here, it's a different lithology. And so we actually have to re-baseline for this interval down in here. Once we've re-baselined and put it all back together, now we've got, the curves overlaying. We did a baseline shift here. And when we did that baseline shift, then we can see the areas that track. That means no hydrocarbons. And now, a lot of petrophysicists don't really like the delta log R. It doesn't follow all the things that they had been taught at university. But if you plot it on a resistivity versus kind of a porosity plot, the baseline intervals form a line with an Archie slope of M, just like with conventional reservoirs. And the delta log R separation shown by the red arrow plotted in a cross plot would show up as in resistivity above that line. So it does kind of fit the same kind of analysis, but there's so much more information that we can see from the overlay, the thickness, how it's changing, and we can better understand the geological environment and how it relates to other reservoirs. So this is one of our calibration wells. We had dozens of them. This is from the North Sea. This is the Kerogen clay that generated most of the oil in the North Sea. And here we've got, the scales up there. One cycle of resistivity is the same as a 50 microseconds. So it's got that slope. And in this case, we can go through and do the overlay baseline here, and we can measure the separation at every point. Maximum separation is somewhere around 0.7. We then we can bring it across to our calibration chart. We have the calibration wells, all the data shown in our 1990, but then we can go in. We know the maturity of this is just entering the oil window, and then we can come off and calculate what's the log predicted TOC and S2 in this case because it's in the oil window. This was a case also from the North Sea, and they took a core, and the geochemists didn't really like this logging approach. So they took core samples every, many samples per foot. And when we plotted it, we see, well, it agrees pretty well. The core plugs, which are 1 inch in diameter, clearly have higher resolution than the logs. The logs combined resolution is probably 2 to 3 feet. But overall, you can identify the interval. We set it up initially using the sonic log because for our geophysical friends, they would run a sonic log in every exploration well from the top to the bottom because they wanted to run synthetic seismograms to do well ties to their seismic. In general, the density and neutron logs are not run over the entire well. So we developed it with the sonic, but we can use these other porosity curves as well with a slightly different calibration. Now, here was a case, and this is from the Duvernay in Canada. It's a Devonian age, where here we can see this high gamma ray shale, but this is a low maturity. It hasn't generated any hydrocarbons, and so the resistivity is really low. The same formation that's in a deeper part of the basin, you can see the resistivity is really high. It's easy to spot this, but in general, you go back and use a different calibration for when it's immature and when it's mature, but you can still see those two major packages of TOC. In this case, it's mature, one on the right, one on the left, it's immature, hasn't generated any hydrocarbons. So the kind of rule of thumb, when it's immature, we get a sonic component in the shale because of the low velocity or long transit time of the kerogen. The resistivity, though, is flat. When it's mature, you get both sides of this. And when we go to over mature into the shale gas realm, you still get some porosity log response, but usually it's in the resistivity. In our 2010 paper, we corrected, we had taken our data at low maturities and we extrapolated it based on one well, but we kind of find that if you actually plug in the equivalent LOM or on the vitrinite reflectance equivalency here, that you would underpredict the TOC in shale gas wells. And we just, until we got into unconventionals, we didn't have much data in the higher maturity, over mature, if you will, gas wells. This cartoon just kind of reiterates that, and I think this is in one of our publications. Just as a quick look, what do you see? How would you interpret it? Now, the field work, when we developed this, again, it was a very fast technique, and it's been applied in the 80s. We applied it to thousands of wells. We'd see someone's publication, we'd go in, we could digitize the logs off their publication, and we could do a DlogR overlay. But this is from Cretaceous age Colorado shale, second white specks. In Canada, it's being looked at as unconventional. But when we look at it and the overlay, it looks like a pine tree. And we kept seeing this, this high TOC decreasing, high TOC decreasing, high TOC decreasing. And we were really wondering what is going on with this. And so a lot of our studies were really related to what is the depositional environment and the building block of these source rocks. In 1985, I was out in the field looking at the Niobrara, which is a big unconventional. This was a down lap on Peter Vail of the one who developed the sea level curves. Kevin Bohax, who's also an exceptional scientist. Earl Kaufman was a professor at the University of Colorado at the time. But then what we saw with this in both the gamma ray and, we see these patterns of these little triangles doing it. And so we came up when, the second paper, Creaney and Passey, a model to kind of describe this. And that a very simple model, you're either in a marine or a lacustrine lake environment. And so you have sediment coming in from land, it'll go out, and as it, with time, you'll kind of fill in the basin with a prograding thing here, a set of things out in, but the terrestrial organic matter, coal, woody stuff is coming in from here. The marine organic matter, the high hydrogen index, is coming out of the things that are living in the ocean. A lot of it will die, fall to the bottom. And if it falls up in here, a lot of times, shrimp and worms and things will eat it, and there's no organic matter preserved. But if you get down into the low oxygen layer, then the stuff is preserved. And also in the low oxygen layer is where you can get uranium associated, preserved with the organic matter. But now we looking at this, if we back up and say, okay, at time zero, our sediment source is 10 to hundreds of miles to the left. And so when we have organic matter that's deposited and in low oxygen, it's preserved. And then with time 1, 2, 3, we're getting progradation, sediments moving closer and closer. And so there's going to be a dilution effect. And that's what we think is what is controlling this. There'll be an apparent deepening, a flooding surface that we see, and the thing will kind of repeat, build again and again. But when we look at this, even though we have high TOC here decreasing upward, what we find when we look at the hydrogen index, again, up high above 400, it's oil prone, below 100, 200 is gas prone because of the type of organic matter. This is the algal material here. And so, and as we get into these, the lower TOC part of the same unit, it's going to be more gas prone, and the oil prone is the basal part. So kind of looking at this in, in Peter Vale's world of, we have a low stand, and this is either eustatic, around the world, or it could be a local. It could be just subsidence, but then we'll get at time A, B, the sea level is higher, and you may get more source rocks forming here that come down and downlap on top. So if you're out here in the basin, you have what is called the maximum flooding surface, and it's at like time C is when that's sea level is the highest. Then sea level or the sediments will start prograding, and there can be a drop, a low stand wedge, and this would become then an erosional unconformity. And we've seen this up in Alaska, where we've got here, we've got the DlogR overlay. This is the HRZ, highly radioactive zone in the Pebble Shale. And here we've got this orange source rock pack here, and we have this blue, and we have this yellow one. And we have a seismic section of this that shows this is downlap on top at North Inagok, which is, a few tens of miles to the north. And then going farther north, we have this, but then we can see, these source rock packages actually downlapping. And so the top of the source rock here is not the top of the source rock here, because we've got additional units that come in. So this was really interesting to understand how source rock units actually build up. Now, when we look at a mudstone or a shale in, this is the Green River oil shale in Wyoming. When we look at it, most of the time, shales don't, they'll become slope formers. But the parasequences that we're seeing here, you know, which is flooding event, progradation, flooding event, they don't look very exciting. You know, now when we start getting near shore, you know, conventional siliciclastic or carbonates, they'll stand out. But here it's kind of boring. Here, this is the Mowry Shale in Wyoming. And this is a case where there was an excellent outcrop. And we went in and took samples up through this parasequence. And again, the eye doesn't really show you what's there. When you start looking at the thin sections, you know, where we've got, these are now low, I mean, this is 10 millimeters is the scale bar. So they're not high magnification. But when you're in the basal part of this, then we've got the laminated organic matter. It's very oil rich. When you're moving up, you're starting to see a little bit of scour from channels. You go up and you have some features that have been squashed. They started out as a circular feature and just the compaction squashes them. When you get near the top of this, in this one parasequence, we start getting evidence of burrowing, and then we may get a top flooding surface where it's exposed and can be carbonate or something else. And all that happens in this one parasequence. Now, when we look at it in terms of physiographic setting, most of the source rocks we look at are on the shelf, you know, coming off a delta and forming there. And there's essentially three different environments. There's the deep basin, and this is like the Monterey Formation forms out here. But most of the time we'll have a ramp. There was an unconformity. And in the case of the Bakken, we've got an underlying carbonate platform that was an unconformity. But then when you go up, then you know there'll be that flooding of that surface, and then sea level will be here, and it'll start filling in, prograding, and you may get this downlapping and the combining of organic rocks. Let's look at this in more detail. So we're up on the shelf. The bottom one is when you've got this sea level kind of covered, went up somehow, whether it was, you know, compaction or subsidence, but when on this extremely flat, eroded shelf, then all of a sudden sea level went up and you start getting organic rich rocks immediately above that contact. Now contrast that with later on, you'll get sea level, first it'll be transgressive and then it'll be progradation as it builds out. But what you'll get there in terms of the TOC, it'll be you'll still have these parasequences. It'll build up to a point of maximum flooding or highest TOC, and then it'll decrease. Where this one is usually the initial entrance into the basin followed by these units. And this you will, in the Bakken, the initial unit is one of these, followed by the upper Bakken, which would be one of these. Now, this is the Horn River Basin, and I use this example to show, number one, TOC against uranium can often be used as a pretty good proxy for understanding, if you have the uranium curve. However, if you're in a lake deposit, oceans have uranium, lakes generally do not. And I'll show an example of an unconventional source rock reservoir that there's no relationship between gamma ray and TOC. But here, this is middle to upper Devonian, so it's similar age to the Bakken, but we've got an underlying Keg River carbonate, unconformity there. All of a sudden, the EV member is put in, and it comes in as high TOC almost to the base. And then later on, as sedimentation occurs, you see we get into the Otter Park member, and there's lots of little subdivisions. But again, you can see the TOC builds, and then as progradation continues, it decreases. And then the Musqueam comes in the Mississippian a little bit later, but we can kind of see these packages. Now, the Mowry Shale is an excellent example of this constructional shelf margin. We've got a reservoir, conventional reservoir, the muddy sandstone here. The Mowry kind of starts, comes up through here, and then goes into the frontier sandstone, which is another conventional reservoir. So we've got a low sand, and then we've got progradation that builds up here, and there's a person there for scale, and there's shadows here also for scale. And then we go back into a conventional reservoir. But this is, again, a tremendous source rock for these reservoirs in parts of Wyoming. Now, when we look at this, again, the muddy sandstone up through the Mowry to the frontier, and this is a case where we get the TOC building to a maximum flooding, which occurs in the middle of the Mowry, and then it kind of TOC decreases above. And again, there's Joe McQuaker for scale. The white units are volcanic ash. So let me show a couple of other examples of this. Let's show another one, which is the platform with the immediately high TOC above it. Again, similar to what you have in the basal Bakken, but this is, occurs in hundreds of source rocks worldwide, where you'll get this and then possibly followed by this kind of a buildup. So this is now the Devonian Exshaw Formation. The Palliser carbonate is an erosional, very flat. And if I plot, we can see, the TOC almost immediately above there is high TOC. And I've put it as a couple of parasequence sets. There may be lots more little parasequences there. The Exshaw siltstone member is the same as Middle Bakken. And so this is, the underlying Three Forks or its equivalent up in Canada. But then, we see this, there is in this location no upper Bakken equivalent. It went to the siltstone member, and anyway, I see I've got a typo in there. I've shown this thousands of times and never caught my typo. Now let's go to a well where we had core. So the underlying carbonate is here. We took a sample, just an inch, a centimeter or two above that, and we're at 13 weight% TOC. And then we even get up to 29 weight% TOC, just a few meters higher. And I'm not sure what the scale here of that is, but we see this. Here's the gamma ray curve from that log. And we can see there are various packages. And overall, there's the flooding surface, a little triangle, another one, another one, another one, and stuff like that. So we can see these basic building blocks of organic rich units, even though in outcrop, we really can't identify it. Nearshore marine, we can, because it goes from, shale to sandstone. But here we go from mudstone to mudstone. Okay, tying to our unconventional reservoirs. And again, I'll show a little bit, but you folks know a whole lot more about the Bakken than I do. I have looked at it, but I'm going to show some other examples, the Woodford, things like that. A lot of times people think, well, shale gas has not been known about, but in upper New York, coming off of the Marcellus, and there'd be gas leaks, and they were first discovered 1669. So shale gas has been known about just from natural leaks. But now let's go in and look at the Barnett Shale using a technique that's called ion milling. This is something that Laux and Reed at the BEG in Texas, Bureau of Economic Geology, first started applying to source rocks. And it was, again, at one of these tipping points. It's a case where now I'm going in, and this is, 1/1000th of a millimeter. So that's 1 micron, essentially. And the thing that we can see is there's a little bit of mica or clay. There's organic matter. There's a pyrite framboid here. But 90% of the rock is silica. This is the Barnett Shale. And you say, well, if it's a shale, it must have clays in it. It has very little clay. But the other thing that this ion milling showed was there's porosity in this organic matter. And I'll come in and talk about it a lot more. But basically, if we're talking about a shale, here we have quartz and plus feldspar. There's total clay here, total carbonate, and shales or mudstones can go from being limestone matrix to pure quartz matrix to there are some that are clay. But there's a lot of these. Now, one of the things in terms of the age, if you look at the geologic time frame here, in the early thing, most of the fine grained sediment was like radiolera, algae. There could have been some sponge spicules, but it was not clays. Clays come around when we started getting a lot more land plants that would hold the material, let it weather to, our familiar illite, kaolinite clays that could be swept into the marine environment. But even, like in the Monterey Formation, it's, 90% silica, and it's from diatoms, of these little sea creatures. But all of this stuff, you do get the carbonates, the coccoliths, and that's what, the Eagleford Shale, the clay-sized particles in the Eagleford Shale are carbonate, coccoliths, and coccolith parts. So when we talk about a shale or a mud rock, we have to forget our concept that, well, that must be a lot of clay minerals. This is an ion milled image of a clay-rich unconventional reservoir. It was in Europe, a project I worked in the early mid-2000s. But this is 10 microns. You can see the clay. You can see framboids of iron in here. But then when we start zooming in, we can see the compacted clay, but we see the organic matter, and we see there are these organic holes or the porosity in there. Now, when we were first looking at this was a lake deposit. So here is the gamma ray, and it is just flat. We did a sonic resistivity overlay, a density resistivity, and then using high resolution density, just using the high resolution pad, not the compensated. We did this, and this is about 2 meters. And then we predicted, here's the TOC. Well, our colleagues, and then over here, I've got the image log and the core photo. But our colleagues, their partner, they didn't believe this was showing where the organic matter was. And so we went in and sampled every few centimeters. And then when we showed them this, they thought, okay, we believe you now, but then, the big question is, well, where are the hydrocarbons stored? It's great to talk about TOC, but, is this, are the hydrocarbons in the non-organic rich? And this is an electrical borehole image, an FMI. bright colors are high resistivity, dark colors are low resistivity. And what we found was then the high resistivity is where the hydrocarbons are, is in the same place as where the organic matter is. And this is water filled. We had, um, you know, when we captured the core plugs, we could measure for the water saturation. And what we found was all of the high TOC stuff is full of water. I'm sorry, is full of hydrocarbons, and all of the low TOC stuff is full of water. And so these are in, right next to each other. But then the source of the gas, if they're trying to produce shale gas, it's you target the high TOC, which is also the high porosity intervals. So let's go look at this. And this is a hypothetical distribution. It's the Barnett Shale. Again, this is 100 nanometers. This is a clay or a quartz particle that is smaller than a clay grain. It's tiny. But okay, so we've got this. We've got things that look like there's, detrital or orthogenic clay here. We've got the organic matter, and we have these holes in it. So when we look at this, and here I'm plotting the size of methane molecules, if you will. They are very tiny. And so all these pores are probably full of oil. All these pores formed in the organic matter. They were never full of water that gas came in and displaced. So where's the water? And the water is probably associated with this siliciclastic surfaces, the clay minerals. And so here we have a system that the gas is trapped in the organic matter. The water is trapped as irreducible water. And then when we go in and frack, we are then connecting up a lot of this untapped gas, and very little water is produced in the typical shale gas. Bring you back to reality. Here is a beautiful photomicrograph of a fine grained sandstone with a beautiful quartz overgrowth. We could imagine there's pore throats in this. There's a pore. We can imagine this was filled with water. Oil came in, displaced it. Gas came in. 50 microns is about the diameter of a hair. This now is that previous picture showing the size of that box, that these things are really, really, really tiny. There was lots of argument. Do we produce any of the adsorbed gas? Is it all adsorbed? Is it all free gas? Coal bed methane. Coal has pores that are about 2 nanometers. So, you can only fit, half a dozen molecules in pores in coal, and then they have to go in and drain the thing, and then they will connect up all these. But in the pores that I'm showing, there's a certain amount that is adsorbed, but as soon as you start producing here, dropping the pressure, these will pop off. And so you will produce adsorbed gas and shale gas as well. Now, this is a real key thing because, and this was in our 2010 paper. I'm going to walk you through this, and but it's like, well, we're getting huge amounts of gas coming out of these shale gas reservoirs. Where, surely these tiny little nanopores, that's not enough gas, to do it. There has to be gas coming from somewhere else. So this one will make you scratch your head, but walk it through me, or let me walk through this. Let's say today, in the overmature case, I've got 5 weight percent TOC. That was from a sample. I can measure it, 5 weight percent. Now, the density of the organic carbon is roughly half that of rock. So then that 5 weight percent being solid goes to about 10 volume percent. So this is what it is actually occupying in the rock, but it's lower density. Now, when we went and I showed, these images, and let's just say, for the sake of argument, 50% of the kerogen or the bitumen is full of holes. That just makes it easier. Then this 10 volume percent of pure TOC would become 20 volume percent of the rock. And if half of that is porosity, then I've got 10 porosity units of gas-filled porosity with no water associated with it. And that is the magic of why we get shale, why we can get so much gas out of these reservoirs that look like they didn't have any porosity at all. So this is kind of a maturity diagram for type 2 kerogen, which is the most common type in the marine environment. And with increasing maturity, we go from solid, we start making oil precursors, bitumen, we start generating oil, then the oil starts getting cracked to gas, and what's left over on the pyrobitumen, it's been cooked away, but we still see it. And the pores that we see are formed in the pyrobitumen and the remnant organic matter or kerogen. So the Bakken reservoir falls right here in, from immature up through the oil window. The Marcellus, Eagle Ford, there's liquids that come out of it, but there's also a lot of gas. The Barnett is well in the gas window. The Marcellus is mostly in here. But like I said, so we kind of understand this. This is a tight oil. This is the Woodford. And TOC, here it's 200 feet thick. We took a lot of samples. And this, again, sits on top of a carbonate platform. So this is that, basal platform, and then followed by these prograding series. But this, I want to show again, it's in the oil window. This is 1 millimeter thin section. The Woodford shale, this was 20 weight percent TOC. In transmitted light or fluorescent light, where the hydrocarbons are is where it's fluorescing, and that's in these Kerogen tasmanides, which is algal material. If I took one of these images and then just made it binary, it comes out that about 40% of this rock is fluorescing, but the TOC was 20 weight percent. And so this is where the multiplying by 2, you take the weight percent, multiply it by 2, because it is, the volume percent is what our logs see and stuff like that, even though our TOC measurements are to weight percent. Now, when we zoomed in to this, again, this is in the oil window. Here's one of these tasmanides cysts, zooming in, and we zoom in, and we couldn't see any organic pores. And so that's where we started saying, well, it looks like the organic pores form, at least in the kerogen, in the latter part, just before when you're starting to go into the gas window. Now, this is the Eagle Ford shale, and there's organic material, organic kerogen, has no pores when it's low maturity, and when you get to higher maturity, and presumably it's bitumen, you get the organic pores. But in the Eagle Ford, you also have other pores that liquid hydrocarbons can go into. So the Bakken is, again, you are more familiar with this than I am, but I will hit it here because we've had a lot of drilling there, and as you've got the three forks, there's unconformity, then you've got that basal organic rich unit, then you've got that silt unit, the middle unit, and then there's a later organic rich unit, and then it goes back into uh, largely carbonates. But yeah, this is a photomicrograph from Julie Lefevre of the geological survey there. We have lower Bakken, organic rich, middle Bakken, upper Bakken, and my understanding is the three forks is on the various benches in it is where most of the production comes from. I haven't worked the Bakken, but we can see the upper and lower Bakken are really high gamma. It's a marine source rock. Again, this one's similar in age to and depositional environment to the X-Shaw that I showed earlier, the middle silt unit, and then the upper unit here, and it's in the Devonian. The source rocks are here. The production, my understanding is it's mainly from these other units. There could be some direct production from the Bakken, and you could enlighten me on what the current thinking is. But when we're talking about porosity systems in shale gas, it's all the porosity in the organic matter, whether it's kerogen or the bitumen. Middle Bakken and Eagle Ford, we probably have pores that contribute to liquid flowing. And these examples were from Jürgen Schieber at Indiana University. So just as a cartoon, places that we'd look to see is the oil, coming out of intergranular porosities, interparticle porosity, or is it actually the oil coming off of the kerogen that's produced or from fractures? I have one more section that I can go into. My time is up. I think I have an additional 10 slides, but if you want me to end here, I can end here and go to questions, or I can go forward. I don't know how long your Zoom meeting, if it cuts you off at 10 minutes after. So this is a good break point. There's a lot of cool stuff coming if you have the time, but if you don't, I've kind of hit the high points of the petrophysics and the geological occurrence of these without getting into numbers. Elias.
I think we have time.
Okay.
Yes.
Thank you very much.
Okay, and because if not, I'll just watch the right-hand side of my screen as people drop asleep or away. Now, this is, I'm going to talk about the GRI crushed rock technique and versus plug porosity. And this was from the Maori study, that we did, where we have organic rich rock, we've got siltstone, and then we've got, sandstone reservoirs. And we had conventional core, we took core plugs, and then we measured the whole core plug helium porosity. It's Boyle's law, send it to core labs or in your own laboratories, and measure the porosity. And typically, at core labs, they have these all automated. It's about 20 minutes that they'll do a Boyle's law helium expansion, and then they'll measure it. So when we're in the sandstone, okay, we're at 12% porosity. And here I have the crushed rock porosity for contrast. But 12% porosity in the crushed rock shows it's 12% porosity. When we're in kind of the siltstone, lower permeability, smaller pore size, there's a bit of scatter, but it's in the kind of 5 to 7% porosity. And the numbers that are on here is the weight percent TOC in the sample. Then we went, but when we have samples from the bottom part here that are laminated organic rich units, that have TOCs of 2 to 3%, and that the core plug porosity is only 0 to 2%, and yet the helium porosity from the crust rock is much higher. And way we can understand this is in a typical flooding thing, Boyle's law, you know, in 20 minutes, if I'm in this very tight stuff, didn't matter if there's a vertical plug, horizontal, you know, the helium only got into maybe a third of that. It never made it through that, you know, 1.5 inch long core plug. So then a very clever person named Don Luffel that I worked with before he retired at Exxon came out with the Gas Research Institute crust rock porosity and permeability. And what they do is they'd take a sample, they would crush it to a certain size, put it in a helium porosimeter. They know the volume of the solids, they know the pressure, and they have a volume here of helium, open the valve, and then they measure how quickly it gets, you know, into these samples. It'll drop down, then the permeability, they could fit it and kind of estimate a permeability. And this all happens, you know, in a matter of minutes. Now, this is Don Luffel. He has since passed away. This is me, more dark hair than gray. And this is Ted Braun, who's a key participant in this. But this was in my office at Exxon. Don came back and visited. We were setting up an SPE round robin to test these labs. But then you can see my well logs from the Marcellus, Eagle Ford, Fayetteville, Haynesville on my whiteboard at the back. And so this would have been in probably 2010 or 2011. But we sent samples out to all the different commercial labs. And the good news is, you know, you would send different samples to different labs. The colors are different labs. And you know, we tried to make them as clear, you know, as isotropic samples, but we see that in general, this one is kind of an oddball, but in general, the different commercial labs would measure the same crust rock porosity to within, I would say, plus or minus 1 porosity unit. That's good news. Now, we sent those same samples to 5 different labs. And note this, this is millidarcy or microdarcy, but each of these is an order of magnitude. And we just kind of said, you know, if you're working with lab green, you'll like, you know, that's 1 microdarcy. Yeah, you know, but the exact same samples from here, the blue, they're down 1, 2, 3, 4 to 5 orders of magnitude less. And so even though they could measure the same porosity, they really couldn't measure the same permeability. And so we said, if you're using a lab, stick with them, don't mix and match. But we went and showed this in an SPWLA meeting in 2011. And then we let the labs, we didn't identify which lab was which. That wasn't our purpose. But we did want to point out the problems. And then I'm going to talk about what ExxonMobil did. And there's some more publications that have since come out. But we just kind of said, for us, and when we asked, what did the different labs do? They said it's proprietary. And I don't blame them. They don't want to, you know, share their technique. But we kind of said, okay, we're publishing this, and we published the results of this in our, I think, 2010 paper. And we just said, there's problems. Now, for the reservoir engineers, you'll love this slide, but I myself am not a reservoir engineer, but what we did is we constructed, we built man-made samples that had, we knew exactly what the capillary tube that went through it. We could measure it. We could calculate exactly what it is. And we put this into 1.5 inch diameter sample as shown here. And it's got, again, this precision capillary tube that we knew exactly what was the permeability of that sample. And we made a variety of these. We also upgraded our equipment with really precision gas pumps. And this is Somnath Sinha and Ted Braun did most of this. I was a co-author. But we tried lots of natural materials and we couldn't find things that were down in the nanodarcy or microdarcy that we could send around. So we had this and, you know, we could measure the permeability of our apparatus and of these samples down to nanodarcy permeability, repeatable. And so here, we had a sample that was about, you know, we did it here. This was the calculated from the diameter of the capillary pressure within this, you know, fake core plug. And the measurements that we got was about 6 versus 13. You know, it's maybe at this, you know, this is nanodarcy. You know, unbelievable stuff. At the high end, we can measure, you know, this is 100,000 nanodarcies. But then when we're down in the 100 of nanodarcies, and we had different samples, and we then offered these samples to any lab. And so many universities asked, you know, can they get these samples? We had loaner samples so that they could test on their equipment. So we know they're not just measuring, you know, leaks in their system, that they're actually making, you know, a measurement of this standard. And so we did this, and then we offered this. And now, and this is my last slide. You know, I'm a geologist. Well, my degree was in planetary science and in geology. It was a dual degree. But I did my field work on the moons of Jupiter and Saturn. And if you look at my publications, there's a lot of NASA publications, because that's what I was doing before I went to Exxon. But I'm a geologist by training, and I'd say, oh, I like porous sandstone, that's my reservoir. Impermeable shale, oh, that may be my source rock. But with this unconventional, this became our reservoir. And so, you know, when we were first starting off with this, and I started working in source rocks in 1982. And then I worked through source rocks all for about 8 or 9 years, 7 or 8 years in the 80s. And I went and worked conventional reservoirs. And then when unconventionals came back, people said, well, this DlogR technique, which just stands for a difference in logarithmic resistivity, can I apply it to shale gas reservoir? And I said, I don't know. So I started looking at it and found, well, it does work to identify the TOC, but we really didn't have the tools to develop, you know, what is the porosity in these systems. Fracking unlocked it. You know, now that we understand this, we understand the parasequence, the building block, which parts are organic rich, how the things mature, how they make their own porosity if needed. And with that, I end. So I thank you. I am open for questions as long as people ask.
Thank you very much, Dr. Passey, for this informative webinar. And thank you for correcting some myths about the shale reservoirs. So Before we go to the questions, I know that some of the attendees are not familiar with the rock evil pyrolysis. So can you please explain that
Yeah.
a little bit? Yeah.
And again, I'm not a laboratory. I'm going to go back to this slide. Is that still displaying full screen?
Yes.
Okay. Rocky valve pyrolysis is a commercial technique. It was originally developed by IFP in France at the university there in Po, but SPWLA and others have written on it. Also, Tissot and Welty, they are geochemists, and this is, but Rocky valve pyrolysis, I have probably a slide in another slide pack, but I'm not going to look for it. But essentially, what they will do is they will grind up an organic rich rock, and then they put it in it's called a bomb that they can heat up, and they will start heating it up at very low temperatures, and then they measure what's coming out of this. And it's been already ground up into a powder by then. But again, it's organic rich material. And if there's any liquid hydrocarbons, as the temperature rises, that'll be flared off and come off as what's called the S1 peak. And then they'll continue raising the temperature, and they will take it up to 600 plus degrees C, where they'll be oxidizing the carbon and actually even burning, converting the carbon to CO2. But in the range of about 400 or 350 to about 450, the kerogen that will remain in the sample, if it's immature, most of the organic matter is this kerogen, but this will artificially mature this kerogen, give it off as a fluid. I mean, it'll come off because of the temperatures, and, as a gas, but it is the stuff that will become the liquids in the reservoir. If in regular maturation it stopped, then we'd have liquid being given off. If they continue to raise the temperature, then this drops off as it all gets converted to gas. And then eventually there'll be an S3 peak, which is carbonate, that they're really turning the thing into carbon dioxide, and there they can get a measure of it. If you go out and Google rocky valve pyrolysis, they'll show you how you can ratio S1 to S2, and you can get a hydrogen index of it, and the oxygen index comes out of the ratio of S3 to, I believe, S2. I'm not sure. I never used that. When you get into the over mature, like that level of organic metamorphism of 10, 11, higher. I mean, the Marcellus is up in here. It'd be vitrinite reflectance above 2. Some other strange things happen. Any carbon goes to graphite. Resistivity drops down. Delta log R doesn't work in those extremely high things. It does work in the lower part of it, but hopefully that kind of explains your petroleum geochemists. They live and breathe rocky valve pyrolysis or their own pyrolysis.
Thank you very much. We actually have a question from Ahmed. He says, in the slide where there is an image log, is it normal for water to be above the gas, or this is an immovable water?
Let me go back to that slide. Okay. And let me bring up all the stuff. Again, this is an unconventional reservoir. This is, looking at the core photo, it's all black shale. There's, in this interval, there's no conventional reservoir. There's no big grains. There's no big pores. And so this is in the interval. Now this did produce gas. It wasn't commercial quantity. But the thing is this is not a reservoir where oil and gas will separate out due to buoyancy. All of the water that is in this clay-rich reservoir and the water up in here is clay-bound water. The hydrocarbons are in the the organic pores and surrounding them here. But again, we had preserved samples up in here, and the water, you could drive it off with heat, but no water would flow out of this. So that's a very different type of environment than a conventional reservoir, as I showed earlier. Here, because your source rock usually is, deeper in the basin, generates, the rock is originally full of water in conventional pores. The oil will come in and displace the water. And if there's gas generated, you can get a gas cap. But in general, oil is lower density than water and will float on it. However, I'm gonna go to a slide that's in my backup. I took it out for time and I still went over. Bad me. But here we go. And when we're talking about clays, when we have kaolinite, this is 10 microns. So they're, again, still much smaller than any sand thing, but we still have, micron to tens of micron sized pores associated with this. With clay, you always get bound water associated with the surface of it. But when we start getting smectite, and illite will convert to smectite. I'm sorry, smectite will convert to illite over time. But that you have the bound water surrounding the clay platelets, but you also have an internal water that is extremely huge. And so this is the clay, this is the water that is in the clay-rich things. And you only can drive it off if you crush it and heat it up and drive it off as a gas. It is bound to that. It will not flow. And it's why when a lot of times you get a shaly sand reservoir, if you have these types of clays in there, you have to do a shaly sand calculation because that water is there, but it'll never flow. Water in the pore space will flow.
Thank you very much. I see Mohammed raising his hand. Please, Mohammed, if you have any question.
Yes. Thank you so much for this presentation. That was great. I actually have like three kind of questions and some information that I want to confirm, if you don't mind.
Okay, no, I don't mind at all. I'm here, like I said, I'm it's now 74 degrees.
Okay, that's good. So you said that first of all, I want to confirm something. Increase in TOC will take from minerals, correct? So if you have higher TOC, that means that you have higher, lower mineral volume, correct?
Yes, what I mean by that is, and I apologize to go back to an example, but I love,
Yes.
So on deposition, and this could be a reservoir. This could be carbonate. This could be clay minerals here. On deposition, we have some mineral composition here. The kerogen itself is deposited at this is the leftover stuff from algae, things like that. It falls out. It is intermixed with this stuff. separated here, but it's, you know, intimately intermixed with it. And so now, once you start generating hydrocarbons, they will go, you know, where the water was and displace it in the regular conventional porosity system. But
So what I
so
want to say is that,
higher TOC will say then the amount of other minerals in the matrix is less.
okay, so that's why the density decreases and slowness increase, because kerogen or whatever is in the organic matter is less stiff and less dense than minerals, correct?
Correct.
So
And also the neutron porosity will be higher because the kerogen has a lot of hydrogen, and the
yes.
neutron porosity, you know, it's really the protons are what slow down the neutrons the most.
So when it comes to resistivity, for example, in Bakken, because it's Devonian, we have high amount of clay. So the resistivity increases too much because we have like the decrease in clay in advantage to TOC. What about if we are in a formation that doesn't have a lot of clay? Do we expect to have like, let's say, smaller increase of resistivity due to a smaller clay content?
Uh, I think what formation are you thinking about, if you can share that?
Let's say, for example, in upper Bakken here, in the organic rich Bakken, we have
Yes.
high clay content. You said that we can have a shale. You see this diagram, 52.
Yeah, and the numbers, I, um, I'm not sure. On your numbers, I took some out. Let me go to my Bakken slides, which, okay. Okay. I mean,
So
now this is just an example. It wasn't anything I worked. But you're saying up in the upper Bakken, you do have clay. Is the lower Bakken primarily a quartz? I don't know the mineralogy of the lower
I think
Bakken.
they are both like 50% clay. And what we said is that increase in TOC increases resistivity, correct?
Only if it's generating hydrocarbons.
Okay, so
It,
what I thought, because I want to confirm that, is that the increase of resistivity, because higher TOC mean lower minerals, so lower clay content, which has bound water. So that's why resistivity increases. So when we have lower clay content, so do we expect to have a smaller resistivity increase due to TOC volume?
um, it all again. I'm hedging because I'm not sure on the things. When I've got very silica rich, well, if I have a lot of clay content, and that's why most shales are around 1 ohm meter.
Okay.
Okay. I
Yeah.
mean, or you know, that's simply because there are clay minerals in there. If it's not organic rich, you know, just putting in organic matter in and of itself does not cause the resistivity to go up.
Okay.
Okay,
Okay, I
and
got you.
yeah, and let me go back. I went over it pretty quick. Uh, hang on, this figure.
Mhm.
This is age equivalent of, or this is the Duvernay, which again is, I think, a Devonian. When it was, when you all you had the organic matter present, but water, oops, I need to click it, but water in there, and I apologize, this doesn't have a resistivity scale, but you know, most shales are around 1 ohm meter, and you know, water filled source rock that has TOC, but until that organic matter, it's low resistivity until it starts generating a non-conductor, which is hydrocarbons. In this case, it's oil. But then when you look, that exact same thing with a similar scale, once you start generating hydrocarbons, man, that resistivity, that water, it could be that this water is still associated with the clay minerals.
Okay. Thank you.
But once you start getting this, then the resistivity really went up. And I think you see that in the upper Bakken as well, unless I'm mistaken.
No, you're correct. So I got this answer. Thank you so much. Also, please, just a second question regarding the maturity. So as we have like an increase in maturity, the kerogen will transform into oil, then gas. So that's why the slowness increases, because kerogen is stiffer because it has shear, correct?
Let me go to this figure just, and let me bring up this. If we have a shale or a clay-rich thing, when it's immature, you have high porosity, okay? And so you would have all the porosity indicators. As you have compaction, the porosity will decrease. And if you had no organic matter, the porosity would tend to decrease during all of this, going from kerogen. I'm only looking at the kerogen here.
No, excuse me, I was talking about slowness.
Yeah,
So
well, the slowness, yeah, well, the slowness of the kerogen density changes as you're going from immature through the oil window.
Yes, 1.4 to 0.8.
Okay, what were the numbers you said?
Density from 1.4 to 0.8 when it goes from kerogen to oil. But like what I want to say is about this is kerogen is more stiff than oil, correct? Fluid. I'm talking about the fluid.
Yes, I mean, and oil, liquid, so you'll have no shear wave going through that. But let me clarify a point. Here, when I'm out here, when it's immature, right before I'm starting to generate any oil, the density of the kerogen is about 1.1 of the kerogen is about 1.1 grams per cc. Okay. Now, when I get out here and starting to go into the gas window, the density of the kerogen, not of the oil, organic matter covers kerogen plus liquids. Okay. But out here, the density of the kerogen, the remaining stuff, is about 1.6 grams per cc. Okay, and so now, but the overall rock, when I'm generating bitumen, which is maybe 0.9 to, on good light oil is 0.6, when I still have all these components in the rock, the kerogen is actually increasing in kerogen density with maturity because I'm breaking bonds and driving off oil and ultimately then gas. So the kerogen itself. Now, once we get these other things, the bitumen, the oil, they're in the porosity and so the density, because I'm generating these lighter products, pushing away water, then the density from your bulk density log, would also decrease as you're moving in this direction.
Exactly.
But it's not because the kerogen is getting less dense, because in fact, kerogen's getting more dense as you drive off the lighter particles.
With maturity?
Yes.
Yeah, I think for the sake of time, we're running out of time and we still have 2 more questions.
Okay.
So, yeah, whenever someone has any question, he can.
Thank you so much for your answers.
And there is a paper that's in the AAPG by oh, shoot, but he was cited in one of my things, and it talked about the density of Kerogen increasing through the oil to gas window. I mean, it was, if you send me an email, I can send you the
Sure. Thank you so much. I
reference.
really appreciate your answers.
Okay, thank you.
Thank you. We still have no more than 6 minutes, and we have 2 questions. So
Okay.
the first question is, can NMR technique be used to estimate the TOC value?
The quick answer is no. There, I mean, NMR is responding to rotating protons, and NMR is really great when you're in the oil window, but when you start getting the Kerogen itself, we had NMR log in that one where we had the image log, and and we couldn't see any effect of it. NMR in the laboratory, you might be able to measure it, and people might be able to get an estimate of total porosity, because the NMR does not see Kerogen, but it will see if there's liquid out there, whether it's in tiny pores or others. So in general, it's no. I have no doubt that people smarter than I have probably figured out a way to work it. But when I was working it, we found little use of it when we're in the shale gas window. In the liquids, yeah, NMR will show the oil, but not necessarily, it won't see the Kerogen.
Thank you. The last question is, what are the mechanisms that control the adsorbed gas in shale gas reservoirs?
That is a good question. When I'm not a reservoir or chemical engineer, and I'm a visual geologist, and all I know is when the adsorption, I mean, it has to do with electrical properties. The same reason you get the water that is adsorbed on silicate minerals, whether they're clay or this, there's a substitution, and most silicate minerals have a negative charge on their surface. And so a water molecule, which is polar, will align itself, and that's what forms the adsorption of water around silicate minerals. In this case, the stuff that's out here in the blue, oops, and I don't know if does my arrow show? Let me go back to my laser pointer. Out here in the blue, this is the Kerogen, and it's, by argument, it is oil wet, even if there's gas in there. And so there's, the stuff has just come out of the solid, and it's going to hang on there because it can line up with the molecules that are in there. But then once it gets, all these sites get full, then it'll pop off and do it. But I'm not, the actual controls on adsorption, I can't explain very well because I'm not a chemical engineer.
All right, thank you very much. Dr. Passey, can you please display your email in the chat box section so anyone can email you if they have any question? Yeah.
Let me look.
With that,
oh, okay. And I now see the chat, and my email is and so that's a tough one to remember.
Yeah. Thank you very much for accepting the invitation. Thank you for the great presentation.
Okay.
Yeah,
I
hope to
I hope you learned something.
Yes, we really enjoyed it. Yeah, thank you very much, and stay tuned for our future webinars. Thank you.
All right. Thank you.
Bye-bye. Thank you.
Bye.